Examples to show the difference between tangential and non-tangential. We start with example that Sheldon mentioned. Example, f of z equal to exponential, and please allow me to write it this way: 1 plus z, 1 minus z, and put the minus there. Sheldon wrote z plus 1 over z minus 1, which is perfectly fine, but please allow me to write it that way. Christina has a question, I think. Hey, Christina.
Sorry, I'm having problems again. So, sorry.
Do you mean that you do not hear the lecture, or?
No. It's that I don't know how to explain. When I want to activate the sound, I'm not able, and the same happens sometimes with the camera.
But do you hear me?
Yes, perfectly.
Okay, thank you. So, do you have a question now?
No.
Okay.
Sorry.
No problem, because I saw in my screen that you raised your hand. I thought there is a...
I'm so sorry. I'm so sorry. I don't know how this happened.
It's okay. I mean, it's, as I said, it's a classroom. We are just chat together. So this function is defined on the open unit disk. It is very simple to see that when we approach to the point 1 on this radius, so here is r, when we consider f of r is exponential minus 1 plus r, 1 minus r, and we see that lim f of r goes to 1 from below is, I mean, this part explodes to plus infinity with minus in front, it becomes 0. This part is easy. A little bit of work, that is not really difficult. I leave it as an exercise for the students. If you consider any non-tangential domain, so C is fixed, but by bigger than 1, still you can show that lim z goes to the boundary f of z, but z stays in the gamma c anchored at 1. Still the limit is 0. It's not that difficult. You need to calculate the absolute value of this, and then you will see again Poisson kernel. But at the end of the day, you see that if you go from inside this gamma c to the boundary, again, the limit is equal to 0. And indeed, this is a good example to see the phenomenon we mentioned before. The phenomenon was that when you change your C, your delta changes too. That's a very explicit formula here. And for this explicit formula, if you write absolute value of f of z less than epsilon and calculate z, you will clearly see that the delta depends on C, and when C grows, delta goes to infinity. So this is okay, this is okay. And the third one show that lim when z goes to 1, f of z does not exist. In other words, the first method, when you go to the boundary without any restriction, is not working here. This part is not difficult to show. It's enough to show that, for example, there is a sequence which goes to the boundary, and the sequence has to be kind of tangential. to point 1, example, find Zn in D such that Zn goes to 1, but f of Zn doesn't go to 0. A sequence here which goes toward the boundary, but when we calculate f of Zn, it doesn't go to 0. So we see here the radial limit was 0 for sure, generalized non-tangential limit was 0. But when you remove the restriction, no, it doesn't exist. So we end up with this limit doesn't exist. And up to here, I mean, all the calculations are elementary. Everybody can do that. What is a bit more difficult, and it's not easy to show, I mean, you need better understanding of Hardy spaces. You can ask this question, well, the limit doesn't exist, but consider all sequences, all Zn in D, such that Zn goes to 1 and lim of f of Zn exists. All such sequences n go to infinity. We know that they exist. I mean, we just saw one specific one here. I mean, any sequence here which goes toward 1 will gives us 0. The boundary limit is equal to 0. So this exists and is equal to 0. So you consider all these sequences, all limit exists, and then put all these limits together. So define a set S. Oh, the naming doesn't matter. The set of all limits n goes to infinity f of Zn. All of these limits. Zn goes to 1. I didn't write it properly. We have to assume that the limit exists, but you understand what I mean. So you collect all the possible accumulation point when you go toward the boundary. You know that 0 is there. Depending on the example I ask here, you may find some other points, but this is a more general question. What is all of them? I mean, if you put them all together. And it's interesting to know that you can approach pretty much everything. It cannot be bigger than that because f of z is less than or equal to 1. I mean, this is not difficult to prove that this function is less than 1 on D. So when you go toward the boundary, it cannot be bigger than 1. But it is interesting to know that when you go toward the boundary, you get everything. So in a sense, you can say it this way. This is a horrible point. It's really a very, I mean, or you can say it's a very interesting point. When you go to that point, you can get anything, all the points of the open unit disk. So this is a topic that I do not enter into a discussion on this, but I just wanted to highlight the fact that even with analytic functions, I mean functions which are very, very nice inside, when you go toward the boundary, something very strange can happen. And this example, just to make you be more surprised, this example is an example for which there is one singular point. There is one point on the boundary which, I mean, is bad, the point 1. There are functions, one of them constructed by Frostman indeed, such that when you go toward the boundary, almost every point is like the point 1. In other words, for almost all points, when you go to boundary, the accumulation point is d bar. This is one thing. And the other one is that when you go toward any point, almost everywhere, the non-tangential limit exists and is unimodular, is absolute value of 1. It's really, if you think carefully about this, it's really counterintuitive. Probably I will comment more about this at the end of the lectures. And now, 2 participants raise hands. If there is a question, please go ahead.
Yes, I have a question. Is there a connection between the last fact we saw and the fact that at 1 the function has an essential singularity?
Yes, there is a theorem for that, which this function I rapidly mentioned is generated by a singular measure, which is Dirac measure, and the Dirac measure is anchored at the point 1. The general theorem says that with respect to that measure, almost all points are like that, are singular points. I emphasize, not with respect to Lebesgue measure, with respect to the measure mu, which represent the function f.
Thank you.
You're welcome. Any further question? Okay. And I said there is a modification of this function, which is interesting. And when we do this modification to Blaschke products has some application. Consider the same function. So this is my example 1, but a bit modified. Still, I call it f. It's not the same f. It's another example. The example we had before, minus 1 plus z, 1 minus z. This was bad at point 1, but consider a multiplier here. For example, a simple multiplier, multiply by 1 minus z. And the exercise showed that this function is nice. In other words, f belongs to the disk algebra. Belonging to the disk algebra means it is continuous at all points of the boundary. Well, if z is not equal to 1, it is trivial. The only thing you need to show is that lim z tends to 1, no restriction. F of z exists and is equal to 1. I think there are 2 comments. Let me see in the chat. If non-tangential radial in z yes. Well, of course, when non-tangential limit exists, radial limit is a special case of that. Is for the case c equal to 1. It has to be the same. And in the context of Hardy spaces, either we consider in H infinity or in HP, this is always the case. Non-tangential and radial coincide. You're welcome. So in this modified example, I ask you to show that if you have a good multiplier, if you multiply by 1 minus z, then you transform your previous function, which had a very strange singularity, to something which is extremely nice. It's in the new function is in the disk algebra. It's continuous at all points of the boundary. For this example, example 1 or example 2, which is the modified version of example 1, we do not need a special tools. It works perfectly well. But if you, there are some more sophisticated example for them we need the definition of Blaschke product. I do not want to enter them here. If there is a time at the end, which I don't think there will be, we can talk about canonical factorization theorem, which is needed in many talks which are coming. But I just write the definition of a Blaschke product, accept it as it is. Details are in the book. If you have a sequence Zn in the D, it satisfies this gross restriction, 1 minus mod Zn is finite. This is a necessary and sufficient condition for this function to be well-defined. Product n from 1 to infinity, Zn minus Z, 1 minus Zn bar Z. This is an automorphism of the open unit disk, since D to D bijectively. If you put Z equal to 0, this combination becomes Zn. The argument of Zn can be a problem. In other words, Zn can rotate infinitely many times around 0. To overcome this difficulty, we multiply here by a unimodular constant to fix that argument. Either some books write e to the I theta n such that theta n satisfy these properties, or we can say mod Zn divided by Zn. And now if you put Z equal to 0, the whole combination becomes absolute value of Zn. And absolute value of Zn, its argument is 0, and the convergence problem is fixed, and this function is well defined. And now assume that these points, I mean, they are in the open unit disk, infinitely many of them, they converge toward the boundary. They can converge either to 1 point, 2 point, infinitely many point, and even in the extreme case, which is the monster which constructed by Frostman, he considered that it can converge to all points of the boundary. And indeed, the construction is not difficult. You consider any positive sequence which satisfies this. For example, Zn equal to 1 minus 1 over 2n, n bigger than or equal to 1. It's better to write Rn. Rn equal to that. I mean, these points are on the radius 0, 1, and they converge toward the point 1. And now you can add some arguments to them. Which argument, for example, Zn equal to Rn e to the I theta n, 1 minus 1 over 2n e to the I, and you choose theta n such that our sequence rotates around the origin infinitely many times and becomes closer and closer to the boundary. For example, e to the in. That works well. This is not the only one, but I mean, there are many options. But let's consider the simple case, something like this. The same phenomenon as before. You can show that when lim Zn goes to 1, it was here. Exactly like this function, you can show that when you go to 1, the limit is equal to 0, not for all Blaschke sequences, but for this one it works. For this one, when you go toward the boundary, the limit of Bn is equal to 0. So if this is our sequence, you can show that lim of Br equal to 0 when R goes to 1. As Paul mentioned, in this setting, radial and non-tangential limits are the same. So either use that theorem or directly show that lim B of Z when Z goes to 1 non-tangentially. Wow, what happened? when z goes to 1 non-tangentially is again equal 0. However, when z goes to 1 with no restriction, p of z does not exist. The limit does not exist. And precisely the same hint I gave here, a bit more difficult, but anyhow, we can fix it. Find a sequence Zn such that Zn go to 1, but b of Zn doesn't go to 0. So it shows that the limit is not does not exist when you go to 1. And the strange phenomenon that we saw for that the exponential function, it happens here too. If we accumulate all the, if we put all the accumulation point in one set, the set is big, is the whole closed unit disk. So this function has the same bad behavior at the boundary 1 as the function before, but at all other points of the boundary, it's a nice function. So the only bad point is here. At all other points of the boundary, the function is nice, it's even analytic. What Frassmann did, he constructed a Blaschke product, call it a monster. So a Blaschke product says that almost all points of the boundary are bad points, are singular points. So this phenomena, this happens at almost all points of the boundary. And at the same time, radial non-tangential limit exists and is unimodular. It's completely counterintuitive what he constructed. Modification that we can do for this function, it is not difficult to show that for any of this Blaschke product, it doesn't matter either this one or with an argument. If Zn goes to 1, or even more general than that, if you define f of z equal to a multiplier, and this multiplier here is z minus 1 times b of z, then lim z goes to 1, f of z is equal to 0. It's not always z minus 1 is the favorite one. Another one is z minus 1 squared, b of z. Don Saracen has a series of lecture notes about corona problem, corona construction, even Douglas algebras. And at the very beginning, it rapidly talks about Blaschke about Hardy spaces to make the set, arrange the setting. And this is the one of the functions that is considered, if I'm not mistaken, over there, for the purpose that it's a function for which f prime belongs to H infinity. F prime is not necessarily if in general the derivative of a Blaschke product is not even the Smirnov class, but if you multiply by this multiplier, it becomes bounded, and it has some interesting applications. I mean, this is not difficult to prove. So this shows the importance of multipliers, and the reason I mentioned multiplying by z minus 1 or z minus 1 squared, because I mean this is as an information. In the Hardy space setting, 0 sets are classified. These are precisely the Blaschke condition here. A sequence is a 0 set of a function in the Hardy space if and only if it satisfies this Blaschke condition. Complete characterization, beautiful point, end of the story. In the Dirichlet space, it's still an open question. There are optimal theorems which says that under these conditions, for example, Shapiro-Schills has a sufficient condition. Under that, we have a zero set. And we can even justify that their condition is optimal. But there is no complete characterization. We have a set of sufficient conditions, a set of necessary conditions, and in between, it's an open question. It is not settled yet. In between, the argument of zeros are important. And in some cases, if you have a good multiplier, like z minus 1 here or z minus 1 squared there, and even some more sophisticated multipliers, you can show that you can form a Blaschke product times that multiplier, the result stays in the Dirichlet space, and you have a zero set. Again, construction of those multipliers are not easy and not trivial. However, the whole question is still an open question, just as an information. Well, this finishes our part about approach region and examples. And now we want to start to talk about representation theorem. To do so, we naturally need to know about LP spaces. I mean, I just mentioned the notation. Sometimes we write LP of T, sometimes LP of M. This is the set of functions which defined on T, measurable with respect to Levesque measure, and integral of f e to the I theta exponent p d theta is finite. And sometimes I hide e to the I theta and d theta and write the same thing as integral over t of f of zeta exponent p dm of zeta. dm is almost d theta, it's normalized. It means that we divide it by 2 pi. And sometimes to emphasize that 2 pi belongs to d theta, we write it as I did. But most of the time, we put it here in front of the integral. So this is a more compact way to write the same thing. And if this is finite, then we take the piece root and we denote it by norm P. And it's a norm if P is bigger than or equal to 1, less than infinity. For P equal to infinity is the essential supremum. And again, it's a norm. Even though we use the same notation for P less than 1, but you need to be careful. For P less than 1, it's not a norm. But I write it here, P less than 1. But in this case, the distance between F and G can be defined as this quantity exponent P. This becomes a metric. And with respect to this metric, the space is complete. It's a fresh space. We do not enter that much into detail of this, but it's better to know, even though all the time, even for P equal to 1, it's something common. I will mention norm of F, but it's not really a norm. Keep this in mind. And also I need the measures, the Borel measures, which are defined on T. So, so M of T is the set of measure mu. Mu is a complex Borel measure. On T. In this case, I emphasize on complex because we define the norm of mu to be absolute value of mu, the total variation of mu on the whole disk. What is the meaning of total variation? This is something that you should have seen in a course on measure theory. If not, I invite you to go and have a look. And also, I emphasize the fact that this is not equal to mu of t absolute value. These are two different things, completely different. Total variation by itself is a measure, and you should master what it means. Well, these are the definition. Why did I mention these two? Because when we studied the representation theorem, two theorems of F Riesz come into play, and we badly need both of them to obtain our representation theorem. The first one is that it says that if P is between 1 and infinity, the exponent conjugate of P is defined by this identity 1 plus P plus 1 over Q is equal to 1. And then Riesz theorem says that the dual of LP is LQ. LP star is equal to LQ. What does this mean? I'm cheating a bit here. The precise formulation is like this. LP star is isomorphically equal to LQ. So there are two technical terms here, isomorphic, isometric, but they are hidden in this identity. Again, to go into further detail, because this is really important for us, given G in LQ, we define lambda from LP to C by the following formula. Lambda of F is defined by integral T F zeta G zeta T and Z. And to emphasize that lambda depends on G, even though G is fixed, it is better to write lambda index G here. Our variable for lambda G is F. F changes over LP. Well, the easy part, I mean, easy depends how familiar you are with measure theory, but the easy part is to show that lambda G belongs to LP star. In other words, it's a bounded linear functional on LP, and also the norm of LG as a linear functional is equal to the norm of G in LQ. I used two technical words, isometrically isomorphic. Isometric is for this one. The norm of lambda G is equal to the norm of G in LQ. This identity reflects in the wording isometric. Isomorphic, which is somehow the difficult part of the theorem and proved by Riesz, says that there is no more. I mean, these lambda G are all bounded linear functionals on LP. So if we make this mapping, lambda G goes into the functional it represents. The second important message of the theorem is that there is no more. This map is bijective. And this part reflects the isomorphism part. So isomorphic, isometric. That's what it means by simply hiding everything in this identity. LP star is equal to LQ. I will need this when we go to study the representation theorem. There is one comment on this lambda g, which I will come back to this a bit later. This doesn't work for p equal to 1. This doesn't work for p equal to 1, but what is the remedy? How we can find a solution for that? P equal to 1, I mean L1 of t. There are two ways to look at elements of L1. One way, we can consider f as a function defined on t with values of the. This is the point of view that we adopted before. The other way is to interpret f as a measure. We defined mu by d mu e to the I theta is equal to f e to the I theta d theta over 2 pi. So we look at f as a measure mu, and with this measure, in this way, we can put a copy of L1 into M. M of t is there. We put a copy of L1 inside M of t, inside the set of Borel measures on t. And again, this is a good copy. In other words, both words that I used before can be used here too. It's isomorphic, isometric. In other words, the total variation of mu, which we saw it's mu total variation of t, is precisely the same as the norm of f in L1 of t. That's the isometric part, and the bijection here, not with all of MT, but just with the image is 1-to-1. Of course, it is onto because we restrict ourselves, but more importantly, it's 1-to-1. So it's a bijection between L1 and a copy of M of t. And with this point of view, we can find a remedy for the problem we had here. This didn't work for p equal to 1. And another theorem, second theorem of F. Riesz that we need here, with the same interpretation that we had before, says that C of t star is M of t. There is a comment. Let me see what is there in the chat. If we take an absolutely continuous Borel measured. Well, yes, but the question is that if we take an absolutely continuous Borel measure, is it represented by f in L1? Well, the answer is yes, but this phrase can be a theorem or can be just a consequence of the definition. It depends how you define absolute continuity. Some people, some authors define mu to be absolutely continuous if it has this form. And so in this case, the thing you mentioned is just a rephrase of the definition. But it's more profound than that. The right definition is that if you have a set of Lebesgue measures 0, then this measure is also 0 on that. If this is your definition, then this phrase is a theorem, and it's not easy to prove that. So it depends how you define absolute continuity, but at the end of the day, the answer is yes. Okay, so that is has done. Yes, okay. So doesn't matter which one you adopt as a definition, but the final answer is yes, even though with the more honest definition, it's kind of difficult theorem to prove. So back to this, and let's finish this. Again, two magic word, isometric isomorphism. You know what it means here with any measure mu. So mu is in M. We can define lambda mu from C of t to C by the formula and the integral over T f d mu. And isometric part means that the norm of lambda mu as a functional is equal to the norm of mu as a measure in M. And the isomorphic part means that if you consider M of t and you project it into C of t star by the formula that we saw above, this mapping is bijective. So again, as before, we have isometric pairing between C of t star, the dual of C of t, and M of t. This is not this I need, and also this one I need in coming lectures. To finish in the last remaining 5 minutes, I would like to make a comment about this representation, this way of defining lambda g, and even this one for lambda mu. This is not the only way, the only method that we can make this pairing. There are several different ways, and each one of them has an advantage. I summarize them here below. The one I wrote about, lambda g of f, it was defined integral over t f g, no, not g bar, g dm. This is good, everything works well. We can say this is definition 1. With this, we saw we have isomorphic isomorphism. Number 2, for some reasons, in particular, when we study the dual spaces of Hardy spaces, some authors prefer to write f g bar dm. This is good. It works perfectly well. We have the isomorphic part. Also, we have the bijection, but note that our mapping here is anti-linear. It really doesn't matter. It's not linear, it's anti-linear, but still the bijection holds. And even, these are not all. I mean, another one, again, for a special reason, that means to take care of the constant that appears in some application. Another way to define lambda g is to define lambda g of f by integral over t. They put a zeta here, and note that our argument is zeta 2 here. Zeta or zeta bar. Anything unimodular here works. There is a reason. It's not just out of, pleasure that we put zeta here. There is a reason the proofs become easier if we put zeta here. The good thing is that even under this definition, isometric isomorphism works. And also the last one, which indeed is not the last one which appears in the literature, it's the last one which I mentioned. This also can be seen in papers. Integral of f zeta g of zeta bar dm zeta. They put bar on the zeta, and when we studied the again the convolution and there are some cancellation with this formulation, it is easier to explain the final result. The same variation which I mentioned, 1, 2, 3, 4 for G, the same variation exists for lambda mu. In other words, you can define, for example, I defined lambda mu of f as integral of f d mu. Sometimes it's better to define lambda mu of f as integral of f d mu and put a bar here. It exists. If you look at the papers, you see such definition. Or put a zeta, lambda mu of f integral of zeta f d mu or d mu bar. All this variation exists in the application. Two things. In a sense, it doesn't matter which of these representation we use. This is one thing. But the important thing is that the variation we use must be compatible. In other words, must be isometric isomorphism. We obtain a good copy of lambda c star or a good copy of lambda p star. If this works, yeah, we have liberty to use the application we are looking for. So this is a kind of summarization of functional spaces that we need. Then I will use this tomorrow to study in further detail the representation theorems. There is something in the chat. Is it better used for the unit circle? What do you mean by general set A? Is this variation I use for the unit circle or the general set A? I mentioned I'm familiar with the open unit disk and upper half plane, and also some Smirnov domains. Such variation exists for the upper half plane and for the Smirnov domain. More than that, more general setting, I'm not familiar with. Well, thank you very much. I think this ends our today's lectures. I'm